for the test on Thursday. The way that test is going to work, it'll be about 50 questions long, maybe a little more than 50. There'll be multiple choice, similar to our quizzes that we've had. You'll have an hour and 20 minutes to take it. People don't usually take that whole time, so, but we won't have anything other than the exam. Okay? You have any other questions about stuff? No. It's covering 0, 1, and then a portion of 2 that I'll notify you of in about an hour. Okay? Some portion of 2. It's not might not go all the way up to page 48 like the quiz did, but we'll get to where we get and then we'll stop. All right? Any other questions? When you get here on Thursday, there'll be a piece of paper on the door that has a map of all the seats, and you'll be in assigned seats. So I'll spread you out. Just find your seat. I'll put some little tabs on the front so you can find your seat. It's like a movie theater, right? A2, A3, that kind of business. But we're not watching a movie. We're taking a test. You're going to show me what you know. Okay? Tests kind of are a big deal, so make sure you're prepared for it, unlike the quizzes. All right. Been talking about pressure. There are a couple different, 3 different sources of pressure. We said that there was the weight of a fluid, which is the source of atmospheric pressure. There's the external force applied to the fluid, which we got into last time. That has to do with Pascal's principle, which is the driving principle behind which device? Pascal's principle. Do you remember? What now? What would you say? Pascal's principle, which describes the force or the pressure on a fluid, that when you apply a pressure on yeah, an external force, that when you apply a pressure to a fluid, that pressure is felt all throughout that fluid. That's the principle behind what device? Balloon popping? Yeah, I guess balloon popping. That when you push on a balloon, it increases the pressure throughout. All right, but the hydraulic lift is really what I was going for. That if I apply a pressure on one side, I get the same pressure on the other side. And I can manipulate those areas in order to get more or less force. Because remember, pressure is force over area. So if I have a small area, then I have a small force. If I have a big area, I have a big force, given the same pressure. Um, okay, we're going to get to interaction of molecules, but first, one last thing. The 3 different pressures that you can measure are gauge pressure. This is just the pressure that the gauge reads. But this isn't an absolute pressure. This is really a differential pressure. A differential pressure. So, like for example, your tires. What is the pressure in your tires? Right, 35 psi. And I don't know what a psi is in a Pascal, but 35 psi is not 100,000 newtons per square meter. It's quite a bit less than 100,000 newtons per square meter. And we know that right here at sea level that we have this pressure. We sort of sit in this ambient pressure of 100,000 newtons per square meter. And so what your gauge pressure is telling you actually is that we're 35 psi above the atmospheric sea level, the pressure at sea level. So it's just what the gauge reads, and it's a difference in pressures. The atmospheric pressure, on the other hand, is the pressure due to the atmosphere. And then the absolute pressure is going to be the sum of those two. So we can talk about the gauge pressure. That's what we usually talk about. That's what our gauges read whenever we're reading pressure. But that doesn't include our atmospheric pressure. So if we want to know the true pressure, if we were at sea level, we would add in that atmospheric pressure. And that would give us the absolute pressure, which is just the sum of these two, sum of gauge and atmospheric pressure. All right, y'all follow me on those three different terms, what they mean? Yep. All right, let's look at the interaction of molecules. We're going to look at the ideal gas law. I think that you've probably had the ideal gas law. If not here at Nichols, you had it in high school, right? PV is what? P what? Right, PV is nRT. It describes the relationship between the pressure, the volume, and the temperature of a gas. So the ideal gas law, we consider a container of gas. If you add gas to the container, the pressure increases. I'm going to just capital P, the pressure increases. If you raise the temperature, the pressure increases. All right, and so we can put together these, there are actually two different laws that combine to join the ideal gas law. And the ideal gas law gives us a relationship between, as I said, P and V. P is the pressure. V is set by the container. So if I think about our container, it has a certain volume. So in this case, if I'm considering this container of gas, it would have a constant volume. And this is equal to N times R times T. So pressure, volume, temperature, and N is the number of moles. That's the amount of gas. And then R is a constant. It's the ideal gas constant, universal gas constant. Um, all right, the units for these are going to be in SI units. Shouldn't be a big issue for us, but I'll just give them to you anyway. It's pascals, cubic meters, Kelvin. We'll talk about temperature scales, I think next chapter, and then the amount of gas is in moles. But those aren't terribly important because we're not actually going to be using the ideal gas law to do any calculations. We'll instead look at how things change. So don't sweat those units. Not something that you really need to know right off. All right. So as I said, the ideal gas law is actually made up of a couple of different laws, and Boyle's law is one of those. And it becomes pretty important in the body because it has a lot to do with how we breathe. Uh, it says that if N and T are constant, then PV, the product of pressure and volume, this should be a capital P, is constant. Right, now let's think about what that means. So if we look at the ideal gas law, it says if the amount of gas doesn't change and the temperature of the gas doesn't change, so physically what that would mean is that you have some outside body that holds the temperature constant, or that the temperature of the gas just because of your surroundings doesn't change that much. So N is constant, the amount of gas, T is constant, the temperature of the gas, and then our pressure and our volume, because this side is constant, these sides are constant. So Boyle's law says that if those two are constant, then the pressure and volume are also constant, or rather the product of the pressure and the volume are constant. And we see this every day when we breathe, that we're constantly changing the pressure and the volume, or rather the volume of our chest cavity, and that allows us to have either a high or a low pressure. So when I breathe in, what happens to the volume of my chest cavity? Am I making it big or small? Don't answer right away. Think about it. When I breathe in, is my chest cavity getting big or small? It's getting bigger, right? And so what that's doing is it's increasing the volume of my chest cavity. Your lungs aren't muscles, right? Your lungs, they don't change shape. It's really just the gas that goes into them that changes their shape. But when you increase the size of your chest cavity, that increases the volume of the container. And so what happens to the pressure inside of your chest cavity? V goes up, P does what? Up or down? It goes down. because the product of P and V have to be constant. If P goes up, then V goes down. So breathing in, the volume of the chest cavity increases, and the pressure decreases. So PV volume goes up. Since it's constant, then that has to go down. All right, so uh, if this value increases, this value has to decrease in order for this to remain to be a constant value. Now, what happens when you breathe out? Y'all try breathing out. What happens to the volume of your chest cavity? It decreases, which causes a bigger pressure. So breathing in, you increase your volume. Out, pressure, volume. Your volume decreases and your pressure increases. Now, if you have your person here, oh, I can never draw a person. Let's see. Y'all get the idea, right? This is a guy. This is a person. And here's his lungs right here. Um, if he has a low pressure in here, that means that air is going to go into his lungs because air will move from a high pressure to a low pressure. Any fluid moves from a high pressure to a low pressure. All right. What happens when he breathes out? He makes the volume what? Big or small? Makes it small. The pressure increases, and then you have air moving from high pressure, which is inside your chest cavity, to low pressure, which is outside your chest cavity. All right. So that we see that with Boyle's law. Um, let's see. I have a video I want to show you. This has to do. Oh, wait. No, wait. I'm sorry. I think I wait. And we're going to wait till we get to the next section. Let's look at pressure in solids. Solids can also experience pressure. I think you might have had a quiz question today about this. So if we think about our pressure, which is force over area, you have two things that are very important: the force that's being applied, and then also the area. So if you have, a small woman in tiny little high heels, or you have a big football player in, just sort of normal shoes, which will exert the higher pressure, do you think? Right, the woman with the heels actually exerts a much larger pressure. You can sort of think about it. Think if they're standing on one leg, or say the lady is just sort of standing on the heel, then she would have 110 pounds. Say the heel has, I don't know, an area of about a half a square inch, then that's going to be 220 psi. Whereas the football player, 200 pounds, and say his foot, I don't know, it's like 15 inches in that direction and maybe 5 inches in the other direction. What's 15? 75. So he has 75 square inches. Well, 200 over 75 square inches, that's approximately equal to 3 psi, right? 3 times 70 is about 200. So there's a big difference in the area here that causes our pressure to be different, even though the force is a lot smaller. Alrighty? The area makes a big deal. The force is important too, but the area makes a big deal. Pressure in solids cause stress, and the stress causes a strain. So in physics and in engineering, they talk a lot about stress and strain. And stress is proportional to the amount of strain. If you want to think of these, stress is like the action, and strain is like the response in the material. So if I stress a material, like watch, I'm going to take this paper with my great strength and bend it. All right. The stress here is the force per unit area that I apply to the paper, and the strain is the deformation of the paper. Or sometimes it'll stretch the material or misshape it in some way, or sometimes it'll just weaken the material, and so it would weaken and eventually break. If you exceed the elastic limit of a material, then that material will break. And we'll talk about in the next section after this exam, there are elastic limits to your bones, and indeed there are elastic limits to the ligaments in your body as well. And if you exceed those elastic limits, then those things will break. All right, let's try these clicker questions. Let's try this one on the left up here first. When you exhale, your chest cavity gets what? All right, no, that's it. And then this causes a what pressure? Can y'all see okay? I think I usually have the lights off. Do y'all like the lights on or off? Does anybody care? Doesn't matter to y'all. Y'all can see okay? All right. All right, we'll go about 8 more seconds. Go to 32. Okay, very good. Your chest cavity gets smaller. That causes a higher pressure. Remember, V goes up, or if V goes down, P goes up. That's Boyle's law. And then that causes you to exhale because you get this high pressure inside, lower pressure outside. Fluids move from high to low pressure. Let's try this one. As one descends to greater depths in a liquid, which of these is true? Feel free to ask your neighbor if you're uncertain or if you just want to check your answer. All right, we'll stop at 23, 25. Okay, good. A is right. As you descend to greater depths in a liquid, the pressure increases. Remember, we came up with this expression. I derived it for you, though you don't need to know the derivation. But P is equal to rho times G times H. So if I go deeper in a fluid, liquid or gas, to a certain H. As H increases, the pressure increases. Also, by the way, if I go deeper in a more dense fluid, then my pressure increases as well. So, like for example, to go up 1 atmosphere is, I don't know, thousands of feet. I'm not sure what 1 atmosphere in pressure is. But if I go into water, are there any divers in the class? You ever dove? Or how far do you have to go in order to get to 1 atmosphere in water? To get to 1 atmosphere of pressure in water is like just 30 feet. So you can get an extra atmosphere of pressure in water because the density is higher by just going about 30 feet. That's why when you go to the bottom of the pool, right, your ears pop and you just sort of feel like you have this pressure pushing in on you because the density of the fluid is so much bigger. Now let's try this next one, the 3 sources of pressure. I got a good joke for you. I was hoping to give it to you on this previous question, but quite got it. All right, we'll stop at say 28. 28. You can go on to the next ones if you want. You're done. Okay, very good. Weight of a fluid, the external force applied to a fluid, that's Pascal's principle. And then the third source is the ideal gas law, molecular interactions within a fluid. Basically, you get these molecules moving around, and if you give them more energy in terms of temperature, that causes them to move around more and interact more, and that increases the pressure. So our pressure and our temperature are related in that way. And then also our volume of our container, our volume of our gas can change as well. All right, let's try this one up here, the one on the right. This is a way to measure pressure. This is called a barometer or manometer. I have two different pressures, one here and one here. How are those two pressures related? Is P1 smaller, bigger, or equal to P2, or is P1 equal to 0? All right, I'm going to stop at 55. All right, we're sort of all over the board, but here P1 is actually bigger than P2. Now remember, if I have a container, y'all, and it's filled with fluid, where is the pressure greatest? At point A or at point B? Where's the pressure greatest? B, right? Because I'm at a greater depth in the fluid. And so a similar thing occurs here. Where is the pressure greatest? Here or here? Is it at point A or point B? Well, it's at point B. And the pressure right here is the same as the pressure right here. Look, you can think about these manometers. Say I have a manometer like this. I have one pressure over here and one pressure over here. The one on the left is pushing down all that fluid and forcing it up on this side. On the other hand, if I had, so in this case, if this was P1, it would be bigger than P2. On the other hand, let's say that I had the opposite scenario where it looked like this. And in that case, P1 on this side would be less than P2 because it's, P2 is pushing down on the right side and forcing that fluid back up. That's how a manometer works. That's how your devices that you use to measure blood pressure work. That's how we measure atmospheric pressure too. It's slightly different with a barometer, but it's the same principle that we're measuring a height of a column of a liquid, and that allows us to calculate then what the pressure is. That's why our pressure measurements are in like millimeters of mercury, centimeters of water, that sort of thing, because that's physically what we're measuring is the height of a column of some liquid. All right, let's try this last one. The ideal gas law there. If you increase the temperature, what happens? The volume decrease, pressure increases, the gas constant, or does nothing change at all? All right. Oops, sorry. Let's stop at 30, 35, 35. All right, good. So here, I like these types of questions where I ask you, if you change this variable, what happens to this other variable? And especially in this section, as we get to the ideal gas law and Poisson's equation and equation of continuity, we have several equations that we're dealing with. I'll be largely asking you not to do calculations, but asking you about the mathematical relationships between these variables. So here, if I increase the temperature, T, everything else remains constant, then the pressure will increase. If both sides have to remain the same, if I increase T, P has to increase because the volume's not changing. Container is still the same. A gas is going to fill a container of any size, right? Uh, the gas constant, it's constant, right? And the amount of gas doesn't change because I have gas in this rigid container. I'm not feeding gas into the container. So if I increase the temperature, the pressure increases. All right, y'all good with those? Sort of, kind of, y'all did okay on them, but make sure that you look over those things. Working through the old test will help. Reading through the books again, looking through the notes. That's what I do when I make out your test. I look in the book, so to make sure we got all the main ideas there. I go through the notes, see what did I emphasize, and then I'll look too at the old exams. And sometimes I'll actually pull questions from the old exams. Not many, 5 or 6 maybe out of your 50, maybe up to 10, but it'll behoove you to look over those old exams. All right, let's look at fluids in motion. Um, this is called fluid dynamics. Whenever we study fluids in motion, and fluids, I think I've mentioned this, but they include all things that can flow. This is an F right here, and that includes liquids and gases. We don't usually think of gases as a fluid, but gases can certainly flow, and the study of fluid dynamics will apply to them. Everything that we've been talking about applies to them. However, we have characteristics of fluid flow that make them either ideal or not ideal, and there are certain characteristics that we'll need to assume that will make for an ideal fluid. Because if you have a fluid that's not ideal, that it just becomes very turbulent and chaotic in the way that it responds, and you have to look at it in a different way. Steady or unsteady, this refers to the velocity of the fluid, and if it's steady, that means that the velocity at a point doesn't change. If it's rotational or irrotational, we're going to look at fluids that are irrotational. That means, they don't rotate. They don't spin around, right? So like, for example, I don't know, what's an example of a fluid that rotates? What? Okay, yeah, tornado. Water, right? Water where? Like in your toilet, when you flush your toilet, it rotates, right? That's a rotational fluid. But we're going to look at fluids that are irrotational. Also, viscous or non-viscous. Which do you think we all want to be concerned with? Viscous or non-viscous? Yeah, you're right, because a viscous fluid becomes pretty complicated. Viscosity of a fluid describes the friction between the molecules. I think there's a C there. Describes the friction between the molecules. And so we'll need to think of fluids that are non-viscous. What are some viscous fluids that you can consider? Think about really viscous. What were you going to say, Amber? You looked excited for just a second. Any viscous fluids? Yeah, Stefan? Huh? What's viscous? Mud? Syrup? Blood. Yeah, we'll treat blood actually as a non-viscous, but yeah, it does have a certain viscosity to it. But we'll consider it, at least for some cases, to be an ideal fluid. But it does have viscosity. Would you say? That oil is pretty viscous, right? It's just thick and it moves slowly. Huh? Molasses, right? So all those are viscous things. Water is a good example of a non-viscous. And then also compressible or incompressible. We're going to think of fluids that are incompressible. That means that when you apply pressure to an incompressible fluid, notes are wrong here. When you apply pressure, the volume stays the same. All right. Incompressible fluids, this is going to get rid of gases. So no gases anymore because gases are compressible. If I apply pressure to a gas, It just gets smaller. It fills the size of its container. It'll get a bigger pressure inside, but the volume will decrease. Whereas a liquid like water or hydraulic oil or whatever, if I apply pressure to them, the volume of them doesn't change. They're incompressible. All right? And then laminar versus turbulent, as I said, this is going to limit us to only liquids. Fluids include liquids and gases, but ideal fluids only include liquids because they're incompressible, and gases are not incompressible. And then finally, I think this is the last one, laminar versus turbulent. We'll consider blood flow to be laminar as opposed to turbulent, though there are instances in blood flow when you do get turbulence. Do y'all know when you get turbulence in blood flow? Good example of it? In the heart, right? When it pumps, you get that, there's a sound. It was like a swooshing sound or something, right? Is it a swoosh? Or what is it? A thump. Is it? No, it's not the thump. It's a swoosh. I don't think it's a thump. Is it? We'll talk about that later. But there is turbulent flow in the body. In laminar flow, the blood flows in parallel layers with no interaction between the layers. So we can think of it as going in these like streamlines. The the fluid flows in streamlines. The layers near to the sides of the pipe may move more slowly. Oh, move more slowly, I'm sorry. And usually this occurs for viscous fluids at low speeds. And as I said, most blood flow is laminar, or we'll consider it to be laminar. All right, if I have a pipe here, we might get slower speeds on the sides of the pipe, or, a blood vessel or whatever, because the fluid will actually stick to the sides just a little bit. But we still get these parallel layers don't interact with one another. They don't move across lines. They keep moving in the same direction forward. And that's in contrast to turbulent flow, where the layers interact unpredictably. The velocity of the fluid changes a lot. If I think about my pipe here, and I've got turbulent flow through it, I got these things sort of just moving around as they move in this direction, but the layers are all a jumble. They all mess around with one another. They all move across these parallel layers. Not a laminar flow, it's a turbulent flow. And when the blood rushes into the heart, you get this turbulent flow. So sometimes blood flow is turbulent, such as in the heart when it contracts. Blood rushes quickly into another chamber. We'll learn what those chambers are. You probably know what they are, and sort of the basics of the heart in the second part of this chapter after the exam. Many of you probably already know that. Okay, let's try these. We'll do the one on the left first. Which of these is not a characteristic of ideal fluid flow? Which of these is not a characteristic of ideal fluid flow? Y'all ask your neighbor, okay? There are 5 or 6 of you that don't have the right answer. Ask your neighbor what they put. It's no shame in that. All right, we'll stop at 48. 48. Okay, good. All of those are characteristics of ideal fluid flow. Remember, we want it to be laminar, not turbulent. We want it to be irrotational, not rotating around. We want it to continue in a straight line. We want it to be steady, not moving quickly and then slowing down, but all at the same velocity. We want it to not be sticky. We want it to be non-viscous. So all four of these are characteristics of ideal fluid flow. And we'll make sort of assumptions about that, but uh, those are the characteristics that we have for ideal fluid flow. Let's look at the right side now. Liquids are which? Compressible or incompressible? And gases are which of those? All right, I'm going to stop at 28. 28. Awesome, that's good. So liquids are incompressible. If I compress, say, water or oil or any other liquid, basically every liquid that you know of is incompressible. It doesn't change the volume of the liquid. It'll increase the pressure in the liquid, right? That's Pascal's principle, but it doesn't change the volume. But every gas that we have is compressible. If you put a gas and you compress it into a smaller container, it'll just go to the smaller container. So liquids are incompressible, gases are compressible. All right, I have a joke for you. You want to hear it? Don't think any poor. This isn't a joke yet, but don't think poor women because it's a little vulgar. And just want. I know you have sort of tender ears, and I don't want to offend you. You ready? What did the blanket say when it fell off of the bed? Oh, sheet. All right, let's look at flow rate. Generally, anytime we talk about what do we talk about? Oh, okay. Anytime we talk about a rate, we mean how something changes with time. So like we'll talk about, the rate of blood flow. We're talking about the speed, like the distance over time, or we can think about uh, the rate of population growth, the rate at which people increase in number over time. So anytime we talk about a rate, we're talking about changes with time. And so flow rate, well, gosh, what does that refer to? It's something over time, but what does it refer to, you think? Well, there's some possibilities. It could just be distance over time, right? It could be like speed, right? Could be speed. What do you think? You think it's speed? It's volume. Man, y'all are awesome. You read the chapter, right? Did y'all read this chapter? Of course, you just have a quiz on it. All right, so a flow rate refers to how a volume, or excuse me, how a, I don't know what I wanted to put here. It's not in my notes. I think it's a volume of fluid changes with time. A flow of fluid changes with time, I think. I'm sorry. Uh, Basically, our flow rate is a volume over time. So our flow rate is volume over time. We ask ourselves the question, at this point, what volume of fluid passes this point in a given amount of time? Is it a tenth of a cubic meter? Is it a hundredth of a cubic meter? There's a certain amount of fluid that passes this point in a given time. And what is that flow rate? If I have an increased flow rate, that means I'm pushing more fluid through that container or through that pipe. Um, in a pipe, the flow rate must be the same in different parts of the pipe. This idea comes about if I have a pipe, and if the pipe is, all the same size, I have a certain flow rate, That is a change in volume over a change in time. Let's say that it's 1 cubic meter per second or whatever. I have it right there. This fluid is going down this pipe. If I'm at some point later down the pipe, then I must also have the same flow rate of 1 cubic meter per second. If I have a lower flow rate at some point later in the pipe, then what's happening? If I have, say, a half a cubic meter per second down at this end, what's happening between here and here? I'm doing what? Y'all know it's, what is it? I have 1 cubic meter per second here. Oh, I'm sorry, this would be a half. I meant to write a half. But if I have a lower flow rate here, say a half a cubic meter per second, what's happening in between? What? The pressure would change, actually. That's not what I'm getting at, though. That's good. But you're right, the pressure does change. I'm losing something somewhere, right? Like I have a leak. I'm losing some flow of material. If if the flow rate was, say, 0.5 here, cubic meters per second, that means that loss of fluid somewhere in the system. And then conversely, if I have an increased flow rate at some point later, that means that I'm introducing additional fluid at some point. So we're going to go along this that we're not taking any fluids out or putting any fluids in, and so then our flow rate is going to be constant. Now, there's an equation. It's called the flow rate equation, or sometimes it's called the continuity equation. I think your book calls it the flow rate equation. And it says that Q1 is equal to Q2, which is what we just said, that the flow rate at one point has to equal the flow rate of the other point. But then it goes on, and it says, look, this is volume over time. Volume 1, volume 2. Volume is area times distance over time. Notice this, d over t, what does that refer to? Distance over time. That's a measure of our, rhymes with read, starts with an S, speed, right. So that is our distance over time is our speed. So the flow rate equation, this on your equation sheet, is that the area of your pipe times the speed of the fluid in your pipe is equal to a constant. So A1 V1 is equal to A2 V2. So like for example, if I have a pipe that's small and then it gets bigger, I have a certain area here. We'll call this A1. I have a certain speed here. We'll call this V1. Down here I have an area A2. What's going to happen to the speed V? Is V2 going to be bigger? V2 down here is going to be bigger, smaller, or the same as V1? It gets smaller, right? Because if the area goes up, the speed goes down. So here our area has gone up, our speed has to go down. So V2 is itty bitty over here. You've seen this with your water hose, I know. Has you ever tried to squirt somebody with the water hose? You want the water to come out faster. So what do you do to the water hose if you want to make it come out faster? What do you do to the cross-sectional area of the water hose? You put your thumb on it. What does that do to the area? Makes it smaller. Makes the water hose go from being this big to just being, you know, like the opening very, very tiny. And that increases the speed, well, not like this. The opposite direction. If I'm coming this here, then my speed would get a lot faster. Yeah, V, the script V here is speed. That's why I wrote up the volume. This is volume. But flow rate is big V over T, which is volume. I'll try to keep those separate, but keep them separate in your mind too. Okay? Now with me on this, folks? It becomes important when we get into the circulatory system because we'll use these ideas to describe how blood flows. All right, let's see what we got. So we'll do a quick little example. So a pipe has a cross-sectional area of 20 square centimeters. Water flows through the pipe at 30 centimeters per second. What is the flow rate in this pipe? So here, flow rate for the first question, what is the flow rate in this pipe? Q is equal to big V over time. That's volume. Look, I'll just write out VOL. The volume is equal to the area times the distance divided by T. And so this is equal to the area times the speed. We went through that same maneuver for the continuity equation, because when I have area times speed, that's the same as the flow rate. And the continuity equation, or the flow rate equation, just says that that flow rate has to remain the same. So Q is equal to A times V. A is 20, V is 30. So that's equal to 600 cubic meters per second. That is my flow rate, 600 cubic meters per second. And then it asks, it goes to a smaller pipe, and I want to know what speed is it now traveling in. So I would say A1 V1 is equal to A2 V2. In fact, this first part I know is 600. We just did that. Is equal to 10 square centimeters times V2. Now, you always, especially on a multiple choice test, you want to always look at the answers and think about, well, this is going from a big pipe to a small pipe. Is it going to be going faster or slower? And you would say, well, it's going to be going, which is that, going from big to small. The area gets small, so the speed does what? It goes up. It's like the thumb on your garden hose. And then it works out here that we see that our V2 is equal to 60. Right? It was 30. When I halved the area, the speed increased to 60. So if I halve the area, I double the speed. You could see on your test some like math problems like this. I'll make the numbers easy, even easier than they are here, just, 2, 4, 6, that sort of thing. So it won't be the numbers that'll trip you up, but you need to know how the flow rate equation works. Okay, right here. Oh, the centimeters per second. So the distance over time. You with me? We don't usually use centimeters for speed, but sometimes when you're doing flow rate, you do. All right. How y'all feeling on this? Test on this on Thursday and kill it, as they say. Is that what they say? I'm not sure who says that. Like 12-year-old boys, I think. All right. Let's see. We talked about viscosity. Um, let's see where we are here. Yeah, we can do this. So viscosity describes how thick a fluid is. Different materials have different viscosities. And your book talks about how temperature affects viscosity. Which are usually more viscous, hot or cold liquids? Cold liquids, right? So usually cold is more viscous. Not always. It sort of depends on the material, but usually, almost always, a cold liquid is more viscous than a hot liquid. The hot liquid, the increased energy of the molecules, they move around more, and they just sort of don't stick to one another as much. The viscosity affects the flow or the flow rate. Viscous fluids like blood need a constant pressure to make them flow. Non-viscous fluids, on the other hand, do not need a pressure, or they just need a minimal pressure. And so we'll look at that in terms of viscosity in just a moment. Superfluids have no viscosity, and they will um, travel through barriers. Actually, you know what? Let's forget about the superfluids. It's not really that crucial, so you can just sort of, it's a little bit in your book about it, but don't worry, you won't have it on the test. All right, let's look at these two questions. Looking at the first one, the flow rate here, Q, which is delta V over delta T, volume over time, has which of these units? If you finish this one, you can go on to the next one. I'm going to skip down for just a second. Y'all keep working. All right. I will stop at 45. Okay, good. A is right. It's a volume over time, cubic meters per second. Make sure you know your units on those things. Think about your SI units, okay? And then now let's try the second one. Water flows with speed V through a pipe whose cross-sectional area is A. If the area is decreased to A over 2, what is the new speed of the water? First ask yourself, does the water speed up or does it slow down? If it speeds up, it'll either be C or D. If it slows down, it'll be A. Or if you think it keeps the same speed, it does not. But if you thought that, it would be B. All right? So that'll help you narrow it down quite a bit. Stop at 48. 48. Okay, awesome. So if the area halves, make it smaller, my speed increases. I always like to draw a picture. My area gets smaller, A goes down, but V goes up by the same amount that A went down. It's a linear relationship. So whatever A does, V does like the exact opposite. So C is right. I would expect some questions like that on the test Thursday. Those sort of relational questions. Let's try this one on the left. When the heart contracts, blood flows quickly from one region to another, causing a distinctive sound heard with a stethoscope. What type of flow is this? Laminar, irrotational, turbulent, or viscous flow? I'm going to stop at 38. Okay, good. C is, oh, wait, no. Is that what I put? Oh, yeah, C, turbulent. I was looking at that other one. Yeah, so it's turbulent. The blood flows into the heart really quickly. The parallel layers, they all intermingle with one another, and it just causes that distinguished swoosh. We thought it was a swoosh. Swoosh. Who's heard the heart? Is it a swoosh? Okay, good. Thank you, sir. All right, and we've already asked this question. It was E. I'm sorry, it was a repeat of a previous question. All right, one last thing. Uh, there's the Poiseuille equation. This we will talk about this more later when we get into the second part of this chapter. But it describes how different variables affect the volume flow rate, particularly for viscous fluids, or fluids that have a certain amount of viscosity. And it looks like this. Don't be blown away by it. It's not terribly complicated, but it's pi r to the fourth times delta p divided by 8. This is the Greek letter eta times L. And so you really need to know what these mean. You're not going to have any calculations with this, of course, but we need to know that r is the radius, So if I have, you know, something that's traveling down, r is just the radius of that object. Delta P is the pressure difference. So I have a pressure P1 down here, a pressure P2 over here. So delta P, if we're flowing in this direction, would be P2 minus P1. It's just the pressure differential. We're always really concerned about the difference in pressure when we're talking about flow rates. And eta is a measure of the viscosity. My daughter's name is Ada, but not after the Greek letter eta. It's the viscosity. A higher eta has a higher viscosity. So maple syrup, next time you have some really thick maple syrup or molasses, you can say, my, the eta for this syrup is extraordinarily high. And people will look at you and like they'll just be amazed by what you know. All right, so that's it's a constant, it's measured experimentally. And then L is just the length. So the length here will be just the length of that pipe. As I said, with the viscosity, if eta goes up, it's more viscous. All right, so all of these affect the flow rate. And so what you need to think about is, well, what happens when you change these variables? So if eta goes up, what happens to the flow rate? Does it go up or down? If this value increases, what happens to Q? It decreases, right? If I increase the denominator, it's going to decrease the flow rate. And that sort of makes sense. If I have a sticky fluid, it's going to flow at a slower rate. Or if I have a longer pipe, that's going to affect the flow rate. If I make my pipe longer, does that increase or decrease the flow rate? It decreases it. So the longer your system is, then it's going to decrease the flow rate. So for example, if eta goes up, Q goes down. If R goes up, Q goes down. On the other hand, if little r goes up, that's the radius. I'm sorry, what was that? R. No, this should be, if L goes up, Q goes down. If R goes up, Q is going to go up not just a little bit, not the same amount, but it's going to go up a lot more because we have this power here, the r to the fourth. So like, for example, if I double r, if I make it twice as big, okay. Yeah, so if I double r, Q increases by 16. Because 2 to the fourth power, 2 times 2 times 2 times 2 is equal to 16. So we'll get into the Poisson equation a little bit more, mainly because I like to say it. Don't you like to say it? Poisson. I didn't know how to say it for a long time, and then a couple of years ago, one of you folks, one of my athletic training majors, told me that it's Poisson. All right, we'll stop there. That's going to be the exam. It'll be up to that page 48. You have any last questions? We have a minute or so if y'all do understand what to do for the exam. Go through your notes, read the book, look at your old test, Dre. No, you'll have the same form that I've been giving you. I really recommend that you use a pencil. I know some of you use pens, but if you have 50 to 60 questions, you're going to make a mistake bubbling. And if you use a pen, you can't change it. So I really recommend that you bring a pencil. No calculators. You won't need a calculator. You'll do some very simple math, but otherwise. All right? All right, let's break. That's all that we're going to do on Thursday is take the exam.